Hello. In this video, I will talk about naming enantiomers. Question is, why do we need to name anything? A more fundamental question, and the answer is obviously, if we want to refer to a material without having to draw its structure or its formula every time, then we have to have a word that stands for that material. Water, for example. We don't want to say H2O every time. We don't want to draw the structure of it every time, so we have to have a name, and the name water is one people have agreed on for that substance. Every other substance we've learned so far has a name. Sometimes a common name, sometimes an IUPAC name, sometimes both. But the point is, when you have enantiomers, they are the same compound, are they not? This one is called sec-butyl alcohol, for example. This one's called sec-butyl alcohol. They both happen to be chiral, but they're not the same as each other, right? They are mirror images, but they're not superimposable, which means that we can put one in one bottle and the other one in a different bottle. And if we want to put a label on it with a name, we can't call them both sec-butyl alcohol. Now, these compounds could also be called 2-butanol, but again, they're both 2-butanol. Sec-butyl alcohol is a common name, 2-butanol is an IUPAC name. But if we want to have a specific name for this enantiomer, how are we going to do that? That's what this lecture will be about. So, there's two ways of doing it. One, and these are sort of historical ways of naming compounds in general, not just enantiomers. One way is based on properties. So, for example, a compound called Sudan red is a red compound, so the property is part of the name of the compound. There are many, many other examples where compounds are named after properties of the compounds, and enantiomers are no different. We can call this one minus sec-butyl alcohol, and this one plus sec-butyl alcohol, because this one happens to rotate plane polarized light to the left, so it's levorotatory. You can also use a lowercase l to stand for levorotatory, so minus and lowercase l mean the same thing as each other. By the way, there's also a system that uses a capital L, but that does not mean the same as a small l. We'll talk about those later. This compound happens to be the dextrorotatory one, or small letter d, or positive. Either of these mean the same thing as each other, but this one's the negative isomer and this one's the positive isomer. And so, based on their properties, that was the name that was given to them, and they're able to be distinguished. This was historically how the compounds were named. But the problem is the optical rotation does not specify the structure. So if you just saw the name minus sec-butyl alcohol, you would not know which of these two structures it was. Or if you just saw that structure, you would not know whether it was minus sec-butyl alcohol. In other words, the property is not directly knowable from the structure, and vice versa. We would like to have a system where you can name an enantiomer based on its structure, not on its optical rotation. In other words, theory rather than data. So this is a system of specifying what's called the absolute configuration. Absolute configuration just means which of the two structures is it. You can specify it by drawing the structure. So this right here specifies the absolute configuration of that particular molecule, but we'd like to have it in a shortened form so that we can include it in name. The basic idea is we're going to call this chiral carbon either capital R or capital S. So one of the enantiomers is going to be considered R, the other one is considered S. So there's a series of rules you have to go through, just like there are with other IUPAC names. So the first rule says list out the 4 groups that are attached to the chiral carbon and prioritize them according to a series of rules. So first, list out the groups. In this case, there's a hydrogen, an OH group, an ethyl group, and a methyl group, all attached to that carbon right there in the middle. Wouldn't be a bad idea to just list them out literally on paper. Hydrogen, OH, methyl, ethyl. And then what you're going to do is, since there are 4 different ones, you're going to give them priority number 1, priority number 2, number 3, and number 4. How do you do that? First thing you do is you look at the atom that's directly attached to the chiral carbon. This is hydrogen. This is oxygen, this is carbon, and this is carbon. And the higher the atomic weight of that atom, the higher priority it is. So of those 4, the hydrogen is the lowest priority. Here's a little hint. Probably 90% of the time when you see a chiral carbon, one of the 4 groups will be hydrogen, and that will automatically be the lowest priority group. So that's number 4. In this particular case, oxygen is heavier atomic weight than carbon is. It's atomic weight of 16. Atomic weight of carbon is 12, and so that's higher. Now, one little thing you might question here is why do we use atomic weight and not atomic number? Well, the reason is because sometimes you can have 2 groups that differ only by the weight of the atom, not by what the atom is. In other words, isotopes, for example, deuterium, which is a heavier isotope of hydrogen, would be higher priority than hydrogen itself. They both have atomic number 1, but one of them is heavier than the other, so that's why we use atomic weight rather than atomic number. So this is obviously the number 1 priority because it's higher atomic weight than hydrogen or carbon. But then the question is, which of these two should we consider to be priority number 2, since they're both carbon? Well, then what you do is this. You list out the other 3 groups that are attached to that carbon. In this case, there's 2 hydrogens and a methyl. You list them in order from increasing weight down. So carbon, hydrogen, hydrogen in that case. The other 3 groups attached here are 3 hydrogens. So you list hydrogen, hydrogen, hydrogen. So, and then you look at where in that list of 3 elements does it differ first. It differs first in this case in the first atom. The carbon is heavier than hydrogen, so this is a higher priority group than this one is, and therefore that's priority number 2, and that's priority number 3. And so those are the rules for prioritizing. Now I'll have to have a few other ones here in a minute. First of all, let's just do some examples. So which of these 2 groups is higher priority? This one might be because it's got 4 carbons. It's a bigger group than this one is, but in fact this one is actually a higher priority. That's because the first atom in both cases is carbon, but this carbon has carbon-carbon-hydrogen on it, whereas this carbon has carbon-hydrogen-hydrogen on it, and so this is a higher priority group. What about these 2? So take a minute and compare this group with this group and see which one's higher priority. Might want to stop the video. So the first atom in both cases is carbon. This carbon has 2 carbons and a hydrogen on it. This carbon also has 2 carbons and a hydrogen on it. So what do you do then? Well, then you look at the next heaviest carbon atom. This carbon has 2 carbons and a hydrogen. This carbon only has 3 hydrogens. So this one is heavier, so to speak, higher priority than this one is. What about here? Well, again, this carbon is heavier than this one. So what we're going to be doing is comparing that carbon with that carbon. And this has 2 carbons and a hydrogen, whereas this only has 2 hydrogens and a carbon. So in other words, the point is, if you can't tell by looking at the first set of atoms, then you go to the next heaviest one and look at its set of atoms. And therefore, this is higher priority. Okay, now there's another sub-rule here, and this gets a little bit weird, the way they decided to do it. How do you handle a carbon that has a double bond in it? Well, basically what you do is you consider this CH is attached to 2 other CH2s. It's double bonded to a CH2, but this carbon you consider as having a CH2 and another CH2 on it along with that hydrogen. So this carbon has a CH2 and another CH2 on it. And then this carbon also has 2 CHs on it. So the second carbon in the string has the original CH and also another CH attached to it. So this group is equivalent to this group. It's as if it has 4 carbons branched in this way. In reality, it's not, but that's how you consider it to do priorities. So basically, this group, the little CH-CH2 group, that is actually higher priority than this big 4-carbon chain or even this branched 3-carbon chain. Why is this higher priority than this branched 3-carbon chain? Well, basically because this carbon has 2 other carbons on it, but this next carbon out has another carbon on it, whereas the next carbon out here doesn't have any other carbons on it. So this is a higher priority group. So let's just practice prioritizing 4 groups. So here are 4 groups for you. What I want you to do is put number 1, number 2, number 3, and number 4 next to them based on which one is higher priority. And number 4 is lowest priority. Okay, so take a minute and do that. Okay, so what are we going to do here? Well, obviously hydrogen's number 4, and then of the other 3, carbon is the lowest weight, so that's going to be number 3. But then which of these 2 is heavier, both being oxygens? Well, this oxygen only has a hydrogen on it, whereas this oxygen has a carbon on it, so this oxygen is higher priority. And there we go. That's, as I said, number 1, that's number 2, that one's number 3, and of course the little hydrogen is number 4. Here's another set for you to work on. Okay, the lowest priority again is the hydrogen. In this case, we have a deuterium. That's the isotope of hydrogen I was mentioning before. It has an extra neutron in its nucleus, so it's a little bit heavier. Still just hydrogen, but its weight is heavier, so it's number 3, the third highest priority. But then among these 2, which one are we going to choose? They're both 3 carbons. They both have a double bond in them. How do we decide which one's higher priority? Well, remember, we look at the first carbon first. This carbon has what attached to it? Well, technically, it has 2 other carbons attached to it because it's a double bond to a carbon. So 2 carbons and a hydrogen, whereas this one has 2 hydrogens and a carbon, and so therefore this is higher priority. So that's number 1, that's the number 2, and so on. Okay, let's prioritize these 4 groups. Okay, well now we have a problem in that none of these is hydrogen, so the lowest priority group isn't a hydrogen here. In fact, all 4 of them have a carbon for their first atom, so then we have to look at the next atom and see which one's heavier. In this case, the next one is bromine. Well, that's way heavier than carbon, oxygen, or oxygen. So this is the first priority. This is the lowest priority because carbon is lighter than oxygen, so that's number 4. But how do we compare these two since they both are a carbon with a hydrogen attached to an oxygen? Well, remember, this is really considered to be 2 oxygens. So this carbon has what attached to it? A hydrogen and 2 oxygens. This carbon has what to it? An oxygen and 2 hydrogens. And so this one is actually heavier because it has oxygen, oxygen, hydrogen, whereas this one has oxygen, hydrogen, hydrogen. So this is higher. So there we go. Oxygen, oxygen, oxygen beats oxygen, hydrogen, hydrogen. So this is higher priority. But bromine beats oxygen, so this is the first priority, and carbon is the lightest of all 4 of these, so that's the 4th priority. Okay, now that we know something about prioritizing groups, the next rule says that you take your molecule in space and you rotate the whole molecule up, down, sideways, whatever you have to do to get the lowest priority group pointing away from you. On a wedge and dotted line diagram, that would mean on the dotted line. Notice that I've drawn this particular structure such that the hydrogen is already on the dotted line, the hydrogen pointing back away from you. So for example, take a look at this one. Notice this one, the hydrogen is not on the dotted line. So what do we do if the hydrogen is on the wedge? Well, now what we're going to do is rotate it. We're going to take this particular molecule and we're going to rotate around an axis right through here. So that hydrogen is going to move around to the back, the methyl group will move around here, and that benzene group will move around to the front. So notice the hydrogen has gone to the back, the methyl group has gone over to here, and this thing has moved out here in front. So take a minute and stare at that and scan your eye back and forth between those two structures and see what's actually happened there. Follow the methyl group, follow the benzene ring group, follow the hydrogen. So we've rotated it now so that the hydrogen is pointing away from you. Okay, here's some other examples of rotating. As we saw before, this hydrogen moves there, methyl group moves here, phenyl group moves there. But what do we do in a case like this, where the lowest priority group is sticking straight up? Well, what I will do, and I've learned how to do this well enough that I can kind of experience, I'm going to take that hydrogen and I'm going to shove it to the back. So I'm going to put my thumb on it and just push it back so that it's pointing away from me. What does that do to the other groups? Well, if this hydrogen moves to the back, that's going to bring this methyl group to the front and move that vinyl group up to the top. So basically I'm rotating it this way. So again, take a minute and stare at this and see if you can see what happened to the OCH3 group, what happened to the CH double bond CH2 group, and what happened to the hydrogen. The point is you need to push it in whatever way you can to get that hydrogen, or whatever the lowest priority group is, to the back. Here's another example. What do we do if the hydrogen is on the wedge like that? Again, just rotate it around. So the hydrogen is going to swing around to the back. The methyl group is going to swing around to this side, and the CD3 group is going to swing around to that side. Now here's some for you to work on. So take a minute and just draw a structure for each of these 3 in which you've moved the hydrogen, or whatever the lowest priority group is. In this case, all 3 of these cases are hydrogen, so hydrogen, hydrogen, hydrogen. Rotate it in such a way that the hydrogen moves to the back. So stop the video and draw 3 structures. We're going to shove that hydrogen around to the back. So we rotate it that way so that it goes to the back. That moves the methyl group over here, and the ethyl group comes to the front. What about here? Well, now we're going to shove that hydrogen to the back. So if you do that, that pops the cyclopentane group up to the top. That swings this CH double bond O group to the front. And what do we do here? We're going to rotate it this way so the hydrogen moves to the back. The fluorine moves around to this side, and this T-butyl group moves around to that side. So again, take a minute and just stare at those and follow the groups and see that you have turned the molecule this way, or this way, or this way, so that the hydrogen or lowest priority group goes to the back. Okay, once you've rotated it, then here's rule number 3. Mentally, or if you want to do it right on your paper, you can, draw a circle around the center. Remember, here's the center of the molecule, from 1 to 2 to 3. Well, if you want to, imagine gripping a steering wheel and turning it from 1 to 2 to 3, whichever way you have to do to go 1 to 2 to 3. So notice in this molecule, that one's number 1, that one's number 2, and that one's number 3. So we go around the center, 1 to 2 to 3, and it's in this case, it's a counterclockwise direction, 1, to 2 to 3. Or if you were to turn your steering wheel that way, your car would turn to the left. And so this is called S. If that rotation is a counterclockwise or turns your car to the left, it's called S. By the way, S stands for synastry, S-I-N-I-S-T-R-E. I think it's a Greek word that means left-handed. It also is the root for our word sinister. And by the way, R, which is what it would be if it was a clockwise rotation, stands for rectus, which means to the right. Now, try this example. You have to do it from the beginning. So you need to prioritize it first, then you need to rotate it, then you need to see, do we go 1 to 2 to 3 clockwise or 1 to 2 to 3 counterclockwise? So work it through from the beginning. First of all, prioritize them. The highest priority among these groups is the bromine because it's much heavier than carbon and hydrogen. Lowest priority is the hydrogen because it's lighter than carbon. But then how do we decide between these two groups? Well, this one is a carbon with 3 hydrogens on it. This is a carbon with 1 hydrogen. Don't forget there's a hydrogen at that carbon. And those polygon figures where the hydrogens are sort of hidden. But it also has 2 carbons on it. So this carbon is higher priority than that carbon is. So that's group number 2 and that's group number 3. So there's the priorities. Then we're going to rotate it so that the hydrogen goes to the back. If we rotate it sort of this way, the hydrogen moves to the back, the bromine moves over here, and the cyclopropyl group moves there. So now the hydrogen's in the back. And 1 to 2 to 3, again, counterclockwise. Therefore, this chiral carbon is S. Okay, now there's some tricks to help you determine absolute configuration. I've gone through the steps, step by step, and you can always use those steps to figure out. But the hard part is the rotating. A lot of people have trouble seeing how the rotation happens in space, so there's some tricks to help you with that. One thing you can do is, if the lowest priority group is not on the wedge, in this case the number 2 is on the wedge, the lowest priority group is the number 4, what you can do is switch those two groups. Just redraw the structure in which you've switched the 2 and the 4, or in this case whatever is on that dotted line, and wherever the 4 is, just switch them. Problem is, when you switch 2 groups on a chiral carbon, you change it from S to R, or from R to S. In other words, you switch its configuration if you switch 2 groups. So in this case, what I've done is I've switched the 2 and the 4, so now it's this way. Now it's easy because the number 4 is already pointing back. I just go 1 to 2 to 3. That's a clockwise rotation, so it appears to be R. What that means then was that the original was S. Okay? So notice that because this appears to be R, 1 to 2 to 3 is clockwise, but we switched 2 groups to get here, it's actually an S. Now, let's look at this structure. In this case, the lowest priority group, the number 4, is on a wedge. So now we don't really have to do any kind of switching or anything. We just go from 1 to 2 to 3. And again, that appears to be a counterclockwise rotation, 1 to 2 to 3. But because the lowest priority group is coming out towards you instead of back away from you, it's the opposite of what it should be. And so therefore, since it appears to be S, 1 to 2 to 3, it's actually R. Okay, now, what if we have a Fisher projection? Can you determine R's and S's on a Fisher projection? And the answer is yes. Notice in this case, the lowest priority group, the number 4, is on a vertical line. And remember, in a Fisher projection, if it's vertical, that means it's going away from you. So these 2 are dotted lines, these 2 are wedges. If it's on a dotted line, in other words, if it's either pointing straight up or straight down, as in this case, then it's easy. Just go from 1 to 2 to 3 around the central carbon, 1 to 2 to 3. In this case, it appears to be S, and since the number 4 group, the lowest priority group, is on a dotted line, it is S. And here, this one, 1 to 2 to 3, clockwise around the center, 1 to 2 to 3. And since the lowest priority group is on a dotted line, it is what it appears to be. So this one was S, and this one was R, which kind of makes sense because these 2 obviously are mirror images of each other, so one should be S and the other one should be R. But there's another problem, and that is, what if the lowest priority group is on the crossbar coming out towards you? Well, then you have to take that number 4 group, the lowest priority group, and shove it to the back. So push that 4 all the way to the back, and what that does is swings the 3 over to here, swings the 1 around this way, and the 2 around this way as well to the front. They're both in the back, but as you push it, it rotates the 2 to the front. And so now the 4 group is to the back. We go 1 to 2 to 3, therefore that's R. Or, here's a trick, you can determine it as it is and realize that it's the opposite. So since the number 4 group is there on the crossbar, that means it's coming out towards you. If we go 1 to 2 to 3 around the center carbon, that would appear to be counterclockwise, isn't it? 1 to 2 to 3, counterclockwise, or S. But because the lowest priority group is on the crossbar, it's actually the opposite, so it's really R. Or there's another way you can do it, and that is, like we did before, switch two groups, and it's the opposite. So since the number 4 group is on the crossbar here, that means it's coming out towards you. Let's switch it onto the vertical bar. So 1 comes down here and the 4 goes up there. Now we're looking at this structure, and it goes 1 to 2 to 3. That appears to be an S, but because we switched two groups, the original must have been an R. Okay. Now, there are other kinds of structural formulas that you can use to determine R's and S's, and these are a little bit trickier, but remember that a chair form like this is a three-dimensional structure, and so if there's a hydrogen, an OH, a carbon with a bromine on it, and a carbon with 2 hydrogens on it, we have 4 different groups on that carbon. That's a chiral carbon. How do you determine if it's R or S? Well, in this particular case, the hydrogen is already pointing away from you, so if the hydrogen is there, then it's easy. Just go 1 to 2 to 3 around that central carbon, and therefore it is an R configuration. It's a little bit harder if the hydrogens are in other positions where they're not already pointing back away from you. Then you have to do some rotations. You have to turn the thing in space, or possibly switch two groups to get the hydrogen so that it is pointing away from you. But we won't be doing very many of those, and so we won't spend much more time on that. What about in a Newman projection? Remember, that's also a three-dimensional structure. It's showing you in space where everything is arranged. So what if you wanted to figure out the configuration of that carbon right there? Again, notice it has a bromine, it has a methyl, it has a hydrogen, and then it has a CH2, CH3 back behind this carbon, CH2, and then a CH3. So a methyl, an ethyl, a bromine, and a hydrogen. Obviously, the bromine's highest priority, the hydrogen is lowest priority, the methyl is number 3, and that group should be number 2. The ethyl group is the second highest priority. So what we're going to do is take that hydrogen, we're going to push it back into the plane. That's going to swing this methyl group down here, the bromine down here, and swing the ethyl group that's back behind there up. And so it becomes 1, 2 to 3, 2 to 3, 1 to 2. And so this would be an R structure. And that's the end of the lecture. Thank you for your attention.